Welcome back, everyone. I'm Jordan Giesecke, and this is The Limiting Factor. This will be the first in a series of videos that cover how Tesla solved the dry electrode process for the 4680 battery cell. Today, I'll be covering a patent application for a plasma treatment process that solved two production challenges: high throughput electrolyte wetting and core collapse of the jellyroll, both of which were likely holding up high-volume manufacturing. Before we begin, a special thanks to my Patreon supporters, YouTube members, and Twitter subscribers, as well as Rebellionaire.com. They specialize in helping investors manage concentrated positions. Rebellionaire can help with covered calls, risk management, and creating a money master plan from your financial first principles. Conventional lithium-ion batteries use a small weight percentage of binder in the electrodes for cohesion and adhesion. Cohesion means that the binder holds the electrode together. Adhesion means the binder allows the electrode to stick to the current collector foils, and to a lesser extent the separator. For battery chemistries used in vehicles, that binder must maintain its structural and chemical integrity over thousands of cycles and for more than 10 years. That means the best binders typically have low surface energy, which means their internal chemical bonds are strong and they don't seek bonds with other chemicals. That makes them slippery, non-reactive, and repellent to most liquids. However, although those qualities add durability and longevity to the battery cell, they create challenges for battery manufacturing, particularly for electrolyte wetting. Let's take a look. After the electrode is coated, it's married with a separator and rolled into what's called a jellyroll. The jellyroll is then inserted into the battery cell, which is then filled with electrolyte. The entire jellyroll must completely absorb that electrolyte because it's what allows lithium ions to travel between the cathode and anode, which is how lithium-ion batteries store and release energy. Binders interfere with that absorption, or wetting process, because they form a smooth, waxy surface on the electrode that repels liquids. That matters because if it takes days for the battery cells to fully absorb the electrolyte, and the factory is producing millions of battery cells per day, it means increased warehousing costs. To avoid that, manufacturers use a variety of tricks to accelerate the absorption of the electrolyte, such as creating a vacuum in the cell before injecting the electrolyte with high external pressure, high temperature filling, laser structuring to create capillary channels, and surfactants to reduce the surface tension of the electrolyte. All of those come with disadvantages. For example, placing the cell under vacuum and then extreme pressure can reduce the stiffness of the electrode by about 50%. That, in turn, can cause the tight inner spiral of the battery cell to unwind, or in the words of the patent application, collapse. In July of 2024, core collapse was cited by Steve Levine of The Information as a major hurdle that the 4680 needed to clear before high-volume manufacturing. It looks like, as usual, solving that problem took longer than expected, but it looks like it was likely solved by plasma treatment of the electrodes. Unfortunately, the patent application didn't precisely explain how plasma treatment solved the core collapse problem, but I have a few guesses. First, the sudden pressure changes caused by placing the cell under vacuum and then high pressure, which I'll call whiplash, could collapse pores in the electrode and separator, weakening them like balloons that have been inflated then deflated. That, in turn, is what might be causing the 50% reduction in stiffness. If the electrolyte was able to wet the electrode without those pressure changes, it could maintain the pore integrity and therefore stiffness. Second, that whiplash could also push and pull on the inner spiral of the jellyroll. That, again, could be avoided by reducing the vacuum and electrolyte injection pressure. Third, as we'll see later in the video, the plasma treatment process causes the electrode to stick to the separator, which effectively glues the entire jelly roll together so that it's less likely to unwind. Fourth, the plasma treatment might also help the electrode stick more firmly to the current collector. That matters because in cylindrical cells like the 4680, as the spiral gets tighter in the core, the stress at the leading edge of the electrode coating can exceed its bond strength with the current collector and cause it to delaminate. Tesla's dry coating process creates an additional challenge here because it's able to create thicker electrode coatings than a typical wet coating process. Although a thicker electrode coating is desirable because it increases the amount of active energy storing material in the battery cell, it's also stiffer and more resistant to bending, which can increase the likelihood of delamination at the core. As a side note, the reason why a wet coating process can't make electrodes as thick as a dry process is because the wet coating mixture is made up of a solvent, cathode particles, and additives. If that mixture is applied too thick, the particles can sink to the bottom of the liquid before it dries, which renders the electrode unusable. The dry coating mixture, on the other hand, consists of particles and binder that form a kind of dough, which carries no risk of stratification. Before we move on, interestingly, the plasma treatment process could also be very useful in a wet electrode coating process. But Tesla discovered the plasma treatment process first as a matter of necessity. That's because the surface energy of the PTFE, or Teflon, that's used in the dry electrode coating process is even lower than the binders used in a wet coating process, meaning it's more resistant to electrolyte saturation and was likely causing Tesla headaches for manufacturing throughput. With all that in mind, let's take a look at Tesla's patent application for the plasma treatment process. The name of the patent application is Method for Enhancing Dry Electrode Electrolyte Absorption and Separator Adhesion and Systems Thereof. It was first published on the 12th of February 2026, and the inventors were Frederick Atadana, Pei Swan Liu, Timothy List, Myri Mahare, and Shubham Patel. I'll link the application in the description if you'd like to look through it yourself. How does the plasma treatment process work? As I said earlier, binder material, especially the PTFE binder that Tesla uses for their dry process, has a stable and non-interacting surface that makes it slippery and repellent to most liquids. In order to make the electrode more absorbent so that it can be saturated with electrolyte, and sticky so that it can adhere more strongly to the separator or current collector, the stable bonds in the PTFE on the surface of the current collector need to be disrupted or modified. But wouldn't the PTFE bonds throughout the volume of the electrode need to be disrupted to allow wetting, not just the surface? No, because as long as the surface bonds are disrupted, capillary action does the rest and draws the electrolyte through the electrode. Tesla's solution to disrupt the bonds, or in their words activate the binder, is to use a plasma made from hydrogen, nitrogen, argon, or oxygen gas. That results in defluorination and hydroxylation at the electrode surface. Beyond those two broad chemical mechanisms, Tesla provides no information on the deeper chemistry involved, so I made the image on screen to illustrate what could be happening. However, I only have certainty that the first panel is correct and the last panel is plausible. The two middle panels are just guesses based on the definition of defluorination and hydroxylation, because depending on the gas used to create the plasma, many different chemical routes are possible. Defluorination means breaking fluorine bonds, which are present in PTFE, and hydroxylation means adding hydroxyl groups. Both of those broad chemical processes can lead to higher surface energy that's better for bonding and electrode wetting. Either way, despite the large number of chemical mechanisms that could be taking place, overall, the plasma treatment process is straightforward, and it surprises me that Tesla appears to be the first in the industry to try it. The difficult part is finding the optimum recipe, so to speak, for a high-throughput production process. In that vein, the patent application lists pages of options in terms of plasma power, temperature, pressure, duration, and flow rate. But, as usual, I'll skip grinding through those details because the options are infinitely variable and what matters most is cost and results. It doesn't appear to be a costly process because in terms of material costs, the gases are cheap and used in extremely low concentrations, such as 0.1%. As for energy costs, the plasma only uses between 200 and 4,000 watts of power, which is minuscule for an industrial process. As for time, it only took 0.1 to 10 seconds using an atmospheric plasma treatment process at several hundred watts. And for a vacuum plasma treatment process, it took up to 20 minutes at 4,000 watts. That is, the atmospheric option was much faster. So it seems to be more promising as a scale-up candidate for industrial-scale battery manufacturing, where line speeds can exceed 100 meters per minute. Next, let's take a look at the results of the plasma treatment process. Figures 4a and 4b show the benefits of plasma treatment for making the jelly roll more structurally robust. It allows the core of the jelly roll to be made smaller without introducing core collapse issues. A smaller core void in the center of the battery cell means more energy storing material and therefore greater energy density. Figure 6d shows electrolyte beating up on an untreated electrode versus 6e, which shows electrolyte being absorbed by a plasma-treated electrode. Figure 7e shows the percent soak, or how fully wetted the jelly roll is versus time for plasma-treated versus untreated cells that were dipped in a beaker of electrolyte. The plasma-treated jelly rolls took about 8 hours to reach 100% wetting, while the untreated were only at about 70% after 15 hours. An extended test showed those untreated jelly rolls took around 72 hours to achieve 100% wetting, so almost 10 times as long as the plasma-treated jelly rolls. Figure 8 requires some context. Typically, after a battery cell is filled with electrolyte and before it goes through formation, the electrolyte is allowed to soak into the jelly roll for several hours to ensure full wetting so that the necessary chemical reactions can occur. Formation is the process of cycling the battery cell to form a protective solid electrolyte interface on the anode. Think of it like seasoning a cast iron pan. It dramatically improves the cycle life of the battery cell, but it does chew up some of the lithium, which slightly reduces the energy density. Figure 8 shows that plasma-treated battery cells soaked for less than 2 hours in electrolyte unexpectedly saw a performance improvement over untreated cells. The finished cell energy increased from 88 to 92 watt-hours, which is about a 4% energy density improvement. Tesla didn't provide any more information than that, and it's quite a surprising improvement. So what's going on here? Honestly, it has me stumped. I have a few theories, but none of them quite fit. So if you're a battery expert, let me know your guess in the comments below. Regardless, the implication here is that with a plasma treatment process, Tesla may have accidentally found a way to squeeze a few more percentage points of energy density out of their batteries, or even skip formation steps. It's difficult to say because Tesla tested treated versus untreated dry-coated battery cells, and we don't have a comparison against wet-coated cells using a conventional formation process. Figure 9a shows that the plasma-treated battery cells also retained more energy on cycling tests than the untreated. It appears that around 100 cycles, the plasma-treated electrode retained 1.1% more energy than the untreated electrode. Again, I'd be interested to see how the dry-coated plasma-treated cell compares to a conventionally produced cell. Lastly, figure 10c shows that separators in contact with the plasma-treated electrode transferred a significant amount of material from the electrode when they were peeled apart, which indicates that the two components bonded. That's as opposed to the untreated electrode where very little material was transferred. This shows the glue-like effect of the plasma treatment that I mentioned earlier in the video, which should improve the structural integrity of the jelly roll. That, in turn, might have positive knock-on effects, like improving the cycle life of the battery cell by reducing the impact of expansion and contraction stresses as the cell is charged and discharged. In summary, necessity is the mother of invention. The PTFE used in Tesla's dry electrode coating process was likely creating greater bottlenecks for electrolyte wetting than a typical wet coating process because PTFE has a greater tendency to repel liquids. That forced them to ditch the typical methods of improving wettability and rethink the wetting process at a first principles level, which led to plasma treatment. Plasma treatment improves electrode wetting to such a great degree that it may allow them to skip process steps like vacuum filling, high-pressure electrolyte injection, and soaking, which would reduce the size of the manufacturing line and cell costs. The plasma treatment process also holds potential benefits for performance by decreasing the core size of the battery cell to increase energy density, reducing energy losses during formation, and improving longevity. Will Tesla receive a patent grant for the plasma treatment process? It looks more likely than any other Tesla patent application I've reviewed. All of the claims in the patent application were considered novel, inventive, and to have industrial applicability. But plasma treatment of the electrode is just one innovation of many that was required to make the dry electrode process work. So as I said at the beginning of the video, in upcoming videos I'll be walking you through a number of innovations that explain how Tesla likely solved the dry electrode coating process. As always, please consider supporting the channel with the links in the description, which now also includes a referral link for Signature Solar. If you use that link to purchase home battery or solar equipment, it nets me a small percent-based credit, but that can add up on a large purchase and it really helps the channel. On that note, a special thanks to my YouTube members, ex-subscribers, and all the other patrons listed in the credits. I appreciate all of your support, and thanks for tuning in.